Hey everyone. So this is a video I've been trying to do for quite a long time now, and I'm trying to get this up before Monday. And it's essentially going to be a really shortened, comprehensive review of everything we're going over in our sessions to hopefully prep you for exam one. Now, I obviously can't predict everything that will be on exam one, but I can try my best, and I've compiled pretty much everything that I think will be on the exam, or at least the main topics that will be on the exam. I'll also be linking other videos that I think are helpful for you guys, and hopefully those should be enough to prep you for your exam. But I highly recommend you look at your professor's notes and any videos they've posted. Um, but other than that, let's just start right away. I don't want to take up too much time with this video. So at the top here, I have 12 C files that I've created. Uh, this is going to be linked in the description below for you guys to download. So I've commented through a lot of these, and we're just going to go through it step by step. I'm not going to be writing any code here. I already have everything pre-written. So everything you see on my screen is going to be as you would have it when you download it. So the first one is just an explanation of a few terms that I use quite frequently. So we have our CPU, which is the central processing unit. We have input-output devices, or I/O devices. We have RAM, which is random access memory, and we have hard disks, or sometimes just called hard drives. The CPU handles all of the arithmetic and the logic of our programs. So anytime we're doing math, that's going to be CPU intensive. It's just a term that if you hear a lot, you know your program is CPU intensive or it's processor intensive. That's what they mean. I/O devices are split into two. So we have input devices. We have like our keyboard, our mouse, and our touchscreen panels. So anytime we're giving input to the computer, that's an input device. And anytime we get a result from our input, that's going to be an output device. So like if we type something and then we see it printed to the screen would be an output device. Random access memory, or RAM, is like short-term memory. So anytime you see code that's being ran, right, it's being ran typically inside of RAM, because all of the information that's stored in that program isn't necessary after the program is done compiling. So I like to think of this like short-term memory. It's things that are only necessary for the moment, while your hard disk and your hard drives, these are like long-term memory. So things that you know at any given time, but you aren't readily accessing. So like your address or your phone number. And this is just essentially on your computer. It's just any files that you have right now that you're not currently accessing. So 2.c is essentially an explanation of Hello World and just a breakdown of every component. So we have our include standard input output library. So when I say library, it's essentially an amalgamation of a bunch of functions in C. So there's a ton of libraries. For intro to C, especially for the first exam, you should only need the standard input output library. There's the math library, which I believe some professors need. And these just have even more functions that you could use here and there. But all you have to really know is that we don't need to call every library. Like I said, there's a lot of them, so it's not really necessary to call all of them. And typically it's also good practice because it shows in whichever piece of code you're writing what libraries are actually used in that code. So if you have a ton of libraries, you might think that this is a really complicated piece of code when in reality it's quite simple. So here I have written that it's just wasted line bloat and it's unnecessary memory that we don't need to actually reference. So below that we have our int main void. So this is a function. We've seen writing separate functions from main, but essentially what you need to know is that it's similar to a function in math, like f of x equals x. So it can take some sort of parameter. The main function typically takes void. You can give it parameters, but for the most part, it should just take in void. Void meaning nothing. We could leave it empty, but typically that's bad practice as it shows that this function might not be complete. You know, maybe you just forgot to put in parameters and that's why it's empty. So typically we put void to denote that this program is done and it takes no parameters. We have these brackets here, which are called code blocks. And these essentially would equal the right side of the equal sign. So everything on that side within the code block would be on the other side of the f of x. So these lines of code, like this printf statement here, is called a statement, and statements must terminate with a semicolon. This tells the compiler, okay, I'm done writing this piece of code, you can go on to the next line. Printf is hosted inside of the standard input-output library, and it takes in a parameter of a string, and strings are denoted by two double colons. And then this is an integer function, which means it has to return an integer value. If this was a double, we would have to return a double value, etc. And we're going to go over data types very short. So all you have to know is that whatever data type the function is, it has to return a value. There's a special one, which is the void function. Just as you can pass something nothing, you can have a void function and return a nothing. So that's just something special. Let's say you want to just have a separate function to print stuff. You could have that and just not return anything from that function. So in 3.c is an explanation of all of the different data types that you'll need for intro to C. So the primary ones you're going to need are ints, longs, floats, doubles, and chars, and even more specifically, probably just integers and doubles and chars. So it changes to just ints. So all of these have something called a conversion code. And in printf, if we want to reference a variable inside of printf, we need to use the specific conversion code to tell the compiler this is the specific data type that's being used here. So for integers, it's %d. For longs, it's %ld. For floats, it's %f. For doubles, lf. And chars, %c. Now, these are pretty self-explanatory. It stands for integer, or decimal is the actual word that it refers to. So I can change this here. F refers to floating point number, and double is a long floating point number. And here I've just put some examples. So below you can already see that integers can only go up from -2 billion to 2 billion. So here are some few examples. They can hold negative values and they can hold 0. Longs can hold much larger numbers. I'm not even going to attempt to say this number, but this is as far as a long can go. Floats and doubles can hold also very large numbers, as you can see. But the difference between these is that doubles are more precise. So even though it's larger in memory, that's what this number is here, typically we almost always want to use doubles simply for precision purposes. It's not worth using a float, because if you're using a lot of floats, you're going to get a large error over time. And then characters, depending on your system, are going to be -128 to 127 or 0 to 255. This is representing every available ASCII character. If you don't know what ASCII is, I recommend Googling the ASCII character chart, and it'll show you all the values a character can hold. And here's just an explanation again why we use doubles instead of floats. And something very important with integers is they do something called truncation, and that's when you remove the floating points after a decimal. So if we look at our examples here, this 6.123456, the point in all these decimals are called the floating points. So truncation essentially just removes that. So if I assign 5.7 to an integer, it just rounds it to 5, even though it should round up to 6, because it sees the decimal place and it chops it off. And it's also just kind of helpful to know that doubles will automatically add 0.0 to the end of any integer that they're given. So if you assign an integer, or you assign a double like 5, it'll automatically change it to 5.0. So here I've just given a few examples. Before we actually start printing these data types, we're going to need to know how we can reference and call them. So these are called variables, and when we create a variable, it's called declaration. And when we assign a variable a value, it's called initialization. So we have, this is the basic layout. You have your data type, so the ones we just learned, and then whatever you want to call that variable. There's a few rules for variables. So number one is that they have to be distinct and that they can't begin with a number. And these are all of the available characters you can use for variable names. So you can use lowercase letters A through Z, uppercase letters A through Z, numbers 0 through 9, and underscores. So here I've listed a few examples. So some good variable names would be like just A, B, and then we have these two different types of cases. So typically people will have their own preference. You can have camel case, which is typically what I use, which is after the first word, every other letter or every other word starts capitalized. So you have, if you were just using one, it would just be like example. If you had two words, it would just be example 2, And if we had another one that had 3 words, it'd be example 2, 3. This is typically how I do it. Some people use snake case, where the first one is the same, but every word afterwards is separated by an underscore, and it's all lowercase. So if I had my third example here, it'd be something like this. It's also important to know that you can have numbers inside of your variables, but they can't start with variables. So here I have some bad examples. Some variable right here is bad because it has no indication of being either of these two cases. So this should actually be something like this, which would be more readable. Another example is to not use all uppercase. So when you use all uppercase, it typically denotes a global variable, which we'll go over a bit later. But that's for later on exams. You shouldn't need to know that for right now. If you start with underscores, that's bad because you might not be able to tell at first glance how many underscores there are. And same goes with having a variable that's all underscores. This is very hard to read. And like I said, you can't start with a number, and you can't use a restricted character. So if they're not within these guidelines, it cannot be declared as a variable name. So here I have some examples of declaration. So there's a few tricks you can do to shorten your code. So instead of having 3 separate integer declarations, I can have them all on one line by separating them with commas. I can initialize them separately on a new line, or I could initialize and declare on the same line. But you can't do this. They have to be unique and distinct. So we already have an integer a, so we can't declare and initialize a new integer a. If we wanted to change the value in a, we would just have to get rid of this line. And we can also do this. So we don't have to initialize everything at the start if we're initializing only some. We can essentially do whichever ones we want at any given time. So in 5.c, we just see an example of printing using format specifiers. So we have integer a, which is just holding a value of 5. We have a long, which is holding greater than the max an integer can hold. So here it's holding over 3 billion. This is actually 3 trillion. We have a float here, which is holding a very large decimal, and this is actually outside of its scope, and I'll show you what that means in a bit. We have a double holding the same value, and we just have a character e, and we see that if we want to add variables in printf, we type in the specific conversion code we need, and then we put a comma and whatever the variable name we're referencing, and it has to be in order. So if I reference an integer first, I need to reference an integer first after the string statement. So here, let's just go ahead and compile this one. This is 5.c. And let's make this a bit bigger here. So it's all in one line. So we have an integer here, which is printing 5. Our long is printing, our float's printing, our double is printing, and our character is printing. And you can see that they both round to 6 points of precision automatically. But if I wanted to specify how many points after the decimal I want it to go, I can use a special character, which is just the period, and then however many points after the decimal I want to go. So doubles can go up to 15. So if I go ahead and compile this again and I print out, you can see that after 6 decimal places, the float prints out random numbers because it's not sure what to print. It's outside of its memory range, so it literally can't hold any more values, while the double can hold as many as it wants. So it prints out its entire value, and then it just pads the rest of them with zeros. So it's just a nice way of showing you how doubles are more precise than floats. So I'll leave this in for you guys. If you want to delete it and just have it back to normal, you can do that yourself. So now that we have our variables, let's learn how we can use arithmetic with them. So we have our basic arithmetic operators, so addition, subtraction, multiplication, division, and mod. So all of these follow PEMDAS, which is obviously parentheses, exponents, multiplication, division, addition, and subtraction. And mod takes the same precedence as multiplication and division. So you can kind of think of it like this. And what does mod do? A lot of people might not have ever seen mod before programming. So what this does is it gives you the remainder of division after you're completely done. So I've essentially written a very long explanation here. So if we look at 26 and we mod it by 3, this results 2. This was a previous answer. we essentially just keep subtracting 3 every single time until we get a negative value, and then the value before that is our answer. And here's just a few more examples. So 10 mod 2 is 0, and that's because we can kind of think of it like 8, 6, 4, 2, 0, and if you reach 0, that's the value. Same thing with 10 mod 3, so we have 7, 4, 1, negative 2, so we can have a negative value, so our value is 1. Same with 4, we have 6, 2, negative 2, our value can't be negative, so it's 2. And 5, obviously 5, 0. And then we have all the arithmetic operators here, so these were just the basic ones, these are all of them. So you have the basic ones here, but you can also attach an equal sign to them to shorten specific commands that you might want to type. So I have an example here of like, let's say I wanted to add 1 to integer a. I could do it normally using just basic arithmetic operators, or I can shorten it. So this plus equals will automatically just add a to the end of this equation on the right side here. I can do something called post incrementation. Oh, so this is post increment, and this is pre-increment. So plus plus is essentially shortened for just plus 1. So you could do it like this or like this, either way. But a lot of people might not also know what post or pre is, so let's go over that really quickly. Yeah, right here. So pre and post are kind of cool, actually. So you're going to see this with for loops, but essentially pre-incrementation is when you increment the value and then use it in an expression, while post is when you use the value first and then increment it. So let's go ahead and show you what that means. So when we use pre-incrementation, we get a value of 6 and 6, but when we use post, we get a value of 5 and 6. So what I'm doing here is I'm creating an integer called a and b, and then I'm doing plus plus b. I'm saying a equals plus plus b. So I've essentially commented out what is being interpreted by the compiler here. So our compiler sees this line of code as pre of b equals pre of b plus 1, and then we're setting pre of a equal to pre of b. While in post, let me change this really quickly. So post of a equals post of b plus plus is seeing post of a equals post of b, and then it's adding. It's like this. So that's just a minor difference. So like, for example, if I just did b plus plus and then I set it equal to a, we'd get the same value, but this is showcasing why we would get different values sometimes. You just have to be careful and double check your work. So now that we're done with that, let's jump back actually to 7.c and just go over some arithmetic. So this file is mainly for you guys. I've essentially written just long explanations using long pieces of arithmetic. So how our compiler would essentially interpret these is by automatically putting parentheses and solving inside the parentheses. But I've also put an example of something you might do by accident. So if you see times equals here, a lot of people might think, oh, just take the value of whatever is being times equals and put it at the front, but that's actually not true. So if we compile this and we do 7.c, we get 25 as our value, even though we should get 11, right? So if you follow this line of logic, it seems this is correct, right? If this was the equation, but it's not the equation. So the way our compiler sees this character is it does the entire right side first, and then it multiplies by 5. So we do the entire right side first, and then at the very end, once we're completely done, we just multiply it by b, and that's how we get 25. So just in case some people might mess that up, it's just helpful to know. It's also helpful to know that you can use the equal sign as an arithmetic sign, and it will read it from right to left. So this line of code right here, it'll see a equals 5, and it'll set a equal to 5. So now that a is equal to 5, it essentially does this. So now it sees b equals a. Well, I just set a equal to 5, so now b is equal to 5 as well. And our compiler now just sees this. It sees c equals b, and it says, well, b is equal to 5, and I can set c equal to 5. So this looks slightly weird, but just know that this is something you can do. This is not a warning, this isn't an error, and you can see we get the same values here. Another common question is, well, if you're dividing and doing a bunch of math, you might end up dividing by 0. So what happens when you do that? If you divide by 0, I get a warning, and it tells me, like, look, you're dividing by 0. And then if you compile, you get a floating point exception core dumped, which is essentially just when you divide by 0. So just helpful to know. So if we go to 9, we just learned arithmetic, so let's learn Boolean or logical operators. So these are all the operators here. I've started like combining it into the code now instead of having separate files for it. So we have less than, greater than, less than or equal to, greater than or equal to, not equals, equals, and or. So I'll go over these last two on the next piece of code. So these are just the basic ones that you should know. You should know that a single equal sign is initialization and a double equals is equals. So when I was using equals here, I'm setting a value of a to 5, right? I'm not checking if the value is 5. If I wanted to check if the value is 5, then I use double equals. And it's important to know that when you're doing logic, a true value is any value besides 0. Oh, any value besides 0. And false is 0. So for example, if I wanted to print the result of 3 less than 5, well, 3 is less than 5, so we get 1. If I wanted to check the value of 5 equals 5, 5 does equal 5, so we get 1. If I wanted to print the result of 3 is not equal to 5, that's true, so we get 1. And if I wanted to print the result of 3 greater than 5, that's not true, so we print 0. And here I've commented essentially that all of these will end up going to 1. And if we go ahead and run this, 9.c, we can see what's happening. So this is 1, this is 1, this is 1, this is 0. And we can see that we can actually use these in arithmetic. And we can set this value equal to 3 to confirm that it's automatically set to a value of 1. So it's just helpful to know that these do end up actually setting themselves equal to 1 after they run. So once this sees 3 is less than 5, this just changes it to 1. So this is most used in if statements. So if statements look something like this. So we have the word if and then a condition if true. So if condition 1 is true, it's going to run the statements inside of this code block. And there's multiple ways you can write if statements. So I could just have it by itself like this to just check a specific case. I could have it with an else if attached. So else if is essentially, we want to check condition 2 if condition 1 is false, and then run its code block instead. And same thing, I can have as many else ifs attached to it as I want. But just know that it has to be attached to an if. It can't just be else if. And then at the end, we can put an else. So if none of these are true, then we just run this one by default. Or we could just have an if and an else by itself, as long as they're attached to each other. So this is the example I've been using for a long time. It's a really good example, but it's blackjack. And it showcases a lot of the logical operators that we just learned. So we essentially, let's compile this. This is 10.c. So let's say I have two players' hands of 17. We can see that they end up tying if we have 17 and 19. Oh, whoops. If we have 17 and 19, we have that the higher hand wins. If we have 19 and 22, I keep forgetting to compile. Let's do 22 and 19. We have that the lower hand wins. If we have 22, not going to forget this time. If we have 22 and 22, that they both bust. So this is just a way of showcasing how if and else's work. So we check if the player 1 is greater than player 2, and then set our high and low hands. And then we check the other case, if player 2 is higher than player 1, and set the high hand and low hand accordingly. And then we have our else. So we want to check to see if we tie or if we bust. So if player 1 equals player 2, then we automatically know that they're the same value. So we only have to check if one of them busts, because we know by default right here that player 2 is going to be the same value as player 1. So I don't have to check if player 2 also busts. And if it does bust, then I print here and I can return early. So some people might not know you can put multiple return statements as long as only one of them is triggered, obviously. But then we also want to check if this isn't true, then by default it has to be a tie. And then if this doesn't trigger, that means we set our hands. So then we just check the hands to make sure that the higher hand doesn't bust. If the higher hand busts, then it ignores this, it goes to the lower hand. If the lower hand also busts, then we just print both players lose. So I recommend, if you're uncomfortable with if statements, just looking at this code more in depth. I'm going to keep on going just for time purposes. This video is already going to be a lot longer than I anticipated. We have the ternary operator. So we just learned about if statements, but we can also shorten if statements in some cases. So the ternary operator takes this code block right here, and it shortens it. So if I wanted to check if a mod 2 equals 0 and then set a value of b to 2 if it's even and 1 if it's odd, I could do it like this. This would be the normal way, but it's quite long. Or I could use the ternary version. So the basic format for it is you have some sort of variable and it equals a true or false question. So d equals c mod 2 equals 0. And then you ask a question like, is this true, right? Is this statement true? If it is true, then put a value of 2 in it. And if it's not true, put a value of 1 in it. And I'm going to go ahead and show you what this would look like. So if we do GCC 11 and we compile, we have b equals 1 and d equals 1. So we can show that both of these end up printing the same thing. It's just depending on whatever you want to use. And I've attached an example of what you would use this for, just in case you wanted to have like a shortened version. So we're checking if the value of I in this for loop is a multiple of 3. Now we're going to go over loops in a bit, but just have to know that if this value right here is 3, then it should print 1, which it does. So 1 is not a multiple of 3, so it's 0. 2 is not, 3 is, 4 is not, 5 is not, 6 is, so it's 1, and etc., etc. You can change this number to whatever you want. But if you haven't seen a loop, what is a loop? So here I have, what are the differences between whiles and for loops? So whiles have the same basic layout as an if statement. So they have while some sort of condition. I'll put condition is true. So while loops will run this code block infinitely until this condition is false. And for loops have 2 additional statements they have. They have an initialization step that they can do, and they have an incrementer step. So I'll show you what this means in a bit. So before we actually look at some code, it's just helpful to know that for loops, you don't actually have to put anything in here. You have to have the semicolons, but you don't have to write anything. While loops do have to have something in there. So if you want to make an infinite loop, you just put while 1 because 1 is a true value, or you could do like while 13 or any value that's just not 0. And I'll go to this common errors thing a bit later. But here I just have some examples. So let's say I wanted to print out a while a is less than 5, right? And then increment it because I need to be able to leave this loop eventually. So let's go ahead and compile this. So here I'm showcasing that both of these are the exact same thing. So let me enter this out so they're a bit separated. Actually, I'll just put like a long comment here. So here I'm showing you what I mean when I say we have an initialization step and an incrementer step. So in this while loop, I'm declaring and initializing this variable to be used in the loop, and I'm incrementing it within the loop itself. So every time this loop runs, I want to do it manually. But in the for loop, I can initialize it inside of the loop, and then I can increment it inside the loop. So this is helpful for knowing just what's being used in the loop at any given time. But I'm just showcasing that these can essentially do the exact same thing. It's just personal preference. I prefer for loops for most cases. There are some cases where using a while loop is better. There's some cases where using a for loop is better. And here's a good example of why would you use a for loop. So for loops are a lot more straightforward, I think. So let's say I wanted to go from 1 to 5 and add up all those numbers. With a for loop, it's really easy to see that at first glance. K equals 1, and I'm going to k is less than or equal to 5. So just like you can declare and initialize variables on the same line, you can do that inside of your for loop. So here I'm initializing multiple variables with a comma separating them, just like I would when I'm using it normally. And here I'm printing out a total, which is essentially just every value of k added together. So k plus 2, or k equals 1, so 1 plus 2 plus 3 plus 4 plus 5, and we get our total of 15. It's also important to know that this k++ step gets used even after the loop is done completing. So that's why we get a value of 6 at the end instead of a value of 5. So that's a common error known as an off by 1 error if you try and reference k outside of this loop. So a lot of common errors are you might forget to uninitialize a, or you might forget to undeclare. No declared I value. So you're trying to use something in your loop that isn't declared. You have a stray semicolon. So every time you have some sort of like parentheses, a lot of times people might just put a semicolon after it. But if you use a semicolon afterwards, your compiler will see it like this, as just a one-lined for loop, and just a random code block afterwards. So obviously this is not the intended goal. Just make sure you don't have a semicolon after your for loop. And you're off by 1. So when I say off by 1, I'm meaning that you're anticipating something and you're off by 1 in that anticipation. So let's say I'm printing out I, and I'm thinking that I'm going from 0 and I'm going to print out every value up until 5, but I end up only printing 0, 1, 2, 3, 4. So that's an off by 1 error, and the correct anticipated result should be less than or equal to, which will give me the right value of 0, 1, 2, 3, 4, 5. No, let me put this back. So below this total example here, I have a pretty good example of why you would want to use for loops. So this is a nested for loop. So just like with the if statements here, I can put an if statement inside of an if statement. I can put for loops inside of for loops. So we went over this in depth during one of my sessions, but the gist of this is if you can understand what's happening here, then you can essentially get any question I would like to think on your exam. So what's happening here is we're printing out this pyramid here. So let's make this a bit bigger. So let's go ahead and just quickly explain why this is being printed. So we're running a loop from 1 to n, and n is 9. And what we're doing on this, on this outer loop here, I'm going to refer to this one as the outer loop, and this is the inner loop. And for simplicity purposes, I'm going to comment this out for now. So we just have this first one. And if we compile again, we only get the first half of this pyramid. So what's happening here is in this first loop, it's just printing 1 through 9. So if I get rid of this loop right here and I compile again, I get 1 through 9. So that's what this outer loop is doing. But it's also doing this inner loop n times. And this inner loop is responsible for all of the subsequent values. So what this is doing is it's saying go from j equals 1 to I every single time this loop iterates and print out that many I values. So on the first loop, j is equal to I, right? So it doesn't run, which is why there's no value here. On the second iteration, iterations are what we call every time you go through a loop. So on the second iteration, j is equal to 1, but I is equal to 2 this time. So now we can print it once, and then 2 is not less than 2, so we only go once. On the third iteration, j is equal to 1, I is equal to 3, so we run twice because 3 is not less than 3. And we do this all the way up until we get to 9. And what the second outer and inner loop are doing is they're doing the exact same thing, but backwards. So just like we typically use plus plus to go up, we use minus minus to go down. And you can see that I'm starting at n this time instead of starting at 1, and I'm going to 1 instead of going to n. And in the inner loop, I'm starting at I, and I'm going until it's less than 1. And I'm essentially just doing the exact same print statements. So this loop right here, if I delete this, is responsible for just printing this bottom half of the pyramid. And I start at n minus 1 instead of n because it would print an additional row of 9s. So I just want it, just for like some symmetry purposes, to just have it print this nice pyramid here. So I just tried to cover like 2 weeks of material in like 30 minutes, so everything might seem a bit rushed, but hopefully this was clear enough for you guys. Like I said, this is going to be linked in the description below for you guys to download all of these files that I've created here. If there's anything else you guys need, let me know. I'm always free for emails, or if you want to schedule a one-on-one with me, I have those available. And obviously my weekly sessions that I have on Monday, Tuesday, and Thursday from 4:30 to 6:30 p.m. But yeah, that should be it for me. I hope you guys have best of luck on your first exam, and hope you guys just ace it. So thank you guys so much for watching, and I'll hope to see you at my next session.